Moving forward with our discussion of chemistry for biology students, we have atoms. An atom is a unit of matter, and it's the smallest unit of matter that can still be said to be of one kind of element. So you can have a gold atom, you can have a carbon atom, you can have a hydrogen atom. But if you take it apart into smaller pieces, it stops being that element. And those smaller pieces that you would take it apart into are subatomic particles. Subatomic means smaller than atoms. So what are atoms made out of? Things that are smaller than atoms, subatomic particles. There's three different kinds that are important for our purposes: protons, electrons, and neutrons. Protons and electrons have something in common. They both have a charge, but they have opposite charges. We call the charge on a proton a positive charge, and we call the charge on an electron a negative charge. If an atom has 3 protons and 3 electrons, then we have 3 positives and 3 negatives, and if we add all of those up together, we end up with 0. They cancel each other out. And when an element has 0 overall charge, we say that it is neutral. And atoms like to be neutral. They feel stable, they feel happy when they are neutral. So most atoms, unless I specify otherwise, unless I tell you it has a charge or something like that, most atoms are going to have the same number of protons and electrons so that they balance themselves out. Protons positive, electrons negative. Protons and neutrons also have something in common. They're both found in the center of the atom, which we call the nucleus, and they both have the exact same mass. Now, when we're measuring mass on this really, really tiny atomic scale, we can't use pounds. We can't use like grams and kilograms. Like the numbers are just too small to use those types of units. So we need a new kind of unit of mass that works on this subatomic level. And since protons and neutrons weigh the same, and that's actually where most of the mass of any atom is going to come from, is the protons and neutrons, we just say that they weigh 1. 1 what? 1 atomic mass unit. Both protons and neutrons weigh 1 AMU, or 1 Dalton is another way to say that. Now, neutrons have no charge. They have a neutral charge. So whereas the proton, positive, has a positive charge, the neutron is neutral. That's why it's called that. Adding more neutrons to an atom can increase its mass, but it doesn't alter its charge. And speaking of charge, one thing that you're going to want to know moving forward is that if you have 2 positive charges next to each other, they want to repel. They want to push away from each other. If you have 2 negative charges next to each other, they want to repel. They want to move away from each other. But if you have a positive and a negative next to each other, they attract. And this probably sounds familiar because this is exactly the same way that magnets work. And in fact, we are talking about the electromagnetic force here. So we are talking about the same sense. Like charges repel and opposite charges attract. So if I just had a proton floating out in space, you could see why an electron might buddy up with it. It might start orbiting around it because they're attracted to each other. Each atom belongs to one type of element, and the difference between 2 atoms comes down to how many of each kind of subatomic particle they possess. Each of the little tiles on the periodic table has a couple of pieces of information about the atom of that element. So we're going to take helium as our example. In the very center of the tile, you'll see the chemical symbol for helium, which is He. If it was hydrogen, it would be H. If it was carbon, it would be C. But for helium, it's He. That's what we use when we're writing chemical equations in order to keep track of which atoms are where. So it's just a placeholder. More interesting piece of information is up here at the top, which we call the atomic number. Now you may remember that from the very end of the periodic table video, where I said that Mendeleev used this idea of the atomic number as a placeholder in his head to justify why certain elements went into a particular position when they really should have gone somewhere else, in order to make sure that all of the elements with the same properties lined up properly. But as it turns out, the atomic number actually reflects the number of protons inside of an atom. So helium is atomic number 2 because it has 2 protons. And the atomic number is the most important feature of an atom. It's its core identity. Every atom with only 2 protons is helium, and all helium atoms have only 2 protons. Atomic number 2 is the same as saying helium. Hydrogen is atomic number 1. All hydrogen atoms have only one proton, and all atoms with only one proton are hydrogen. Carbon is atomic number 6. All carbon atoms have 6 protons. All nitrogen atoms have 7 protons. All oxygen atoms have 8 protons, and so on and so forth. The atomic number, the number of protons, is the identity of the element. The number of electrons and the number of neutrons can be different from atom to atom within the same element, but the protons are always the same. Now, at the bottom of this little tile, there's another number, and this number is the atomic mass. This is how much, if we had a really, really teeny tiny scale to put this atom on, what mass reading we would get, how much it would weigh, essentially. And you can see here that helium has an atomic mass of 4. Now, we know that each proton weighs 1 atomic mass unit, okay? So out of the 4 that it weighs, half of that mass is coming from the protons. 4 minus 2 gets you 2. Where's the rest of the mass coming from? Well, neutrons also weigh 1 atomic mass unit, and electrons, they do have a very, very tiny amount of mass, but the mass of an electron is so teeny, tiny, insignificant, and trivial that not even chemists worry about how much an electron weighs. Only particle physicists worry about how much mass an electron has. It's very, very trivial, and so we're going to pretend that the mass of an electron is 0. So there's only 3 particles inside this atom. We know that the 2 protons weigh 2, and then we know that the mass of the electrons is not important at all, and the total mass is 4. So what is the mass of neutrons that we have left over? Well, 4 atomic mass units minus 2 atomic mass units, 1 per proton, gives us 2 remaining. Since we know that every neutron weighs 1, that means there must be 2 neutrons to account for the mass. So I know that was a lot all at once, especially for any of you who haven't had any chemistry before. Let me simplify it. A helium atom weighs 4. That's what this number is at the bottom. It's the atomic mass. The protons, which we know from the atomic number, weigh 2. You subtract the atomic number from the mass, you get 2 left. Those 2 is how many neutrons you have in that atom. And the neutrons and the protons go in the center of the atom, in a little cluster that we refer to as the nucleus of the atom. Now later we're going to talk about cells, and there will be another structure that we call the nucleus, so don't get them mixed up. But the very center of an atom, where all the mass is the nucleus of that atom. How do the electrons fit in? Well, electrons do not go into the nucleus. Electrons actually hang out around the perimeter of the atom. Now, there's no information on this card that directly tells us how many electrons there are. However, unless I tell you otherwise, you can assume that an atom has an overall neutral charge. And that means that the number of protons and the number of electrons will be equal. So if there's 2 protons, there must also be 2 electrons, and they go into these electron shells around the outside. Here, they're shown kind of orbiting around like planets around a little solar system, which is not accurate, but it is a very convenient way to think about electrons. Before we go any further, I want to make sure that you're all comfortable with this content, so I want you to pause the video and try these problems on your own. Given these 3 tiles from the periodic table, and I just took the leftmost column and took the first 3 tiles that were on there, how many protons, neutrons, and electrons would you expect in the atoms of each element based on that information? I took the liberty of rounding the atomic mass to the nearest integer, so you don't have to think about any of the remainders or anything like that. Just how many protons, neutrons, and electrons would there be? Pause the video now and try your hand at these problems. So hydrogen is the easy one. It's got an atomic number of 1, and it's got an atomic mass of 1 as well. So the atomic number is the number of protons. It's 1, so hydrogen has 1 proton. Every proton weighs 1 AMU, therefore we already have all of the mass of this atom accounted for, so hydrogen has 1 proton, no neutrons. How many electrons? Well, I didn't say that it was a charged atom, so you should assume it's neutral, so it'll have the same number of protons as it does electrons, therefore 1 proton, 1 electron, and 0 neutrons. Lithium is a little bit harder, but it's not too hard. It has an atomic number of 3, so that means it has 3 protons. And it's got a mass of 7. 7 minus 3 is 4, so we have 4 neutrons to worry about. 3 protons, 4 neutrons, and again, it's neutral, so there's going to be 3 electrons as well. And then we have sodium with atomic number 11. And it weighs 23 AMU, so we know that 11 of that AMU comes from the protons, 12 must come from neutrons, and then we will again assume that there's an equal number of protons and electrons. Electrons are a lot more capricious than these other subatomic particles are. Atoms gain and lose electrons constantly. So although in these examples we have the same number of protons and electrons, that's not always the case. We'll talk about that more later. And speaking of those troublesome electrons, as it turns out you can't fit all of your electrons into one electron shell. Every electron shell only has enough space for a certain number of electrons, and if you add more and more electrons, you need more and more shells in order to fit them all in. Since different elements will have different numbers of electrons, that means the number of shells between two atoms might also be different. But those electron shells get larger and larger in a predictable way. So, starting with the simplest element, hydrogen. Hydrogen has 1 proton and 1 electron, so it only needs 1 electron shell to fit that electron in. Helium has 2 protons, and therefore it has 2 electrons, and it turns out that first electron shell can fit 2 electrons, so that's fine. Hydrogen and helium both only have 1 shell. But that shell is very small, and it can only fit those 2 electrons max. So if we move up to the next heaviest element, lithium, with 3 protons, it has 3 electrons as well. In order to fit in that 3rd electron, we have to create a new place. We need to create a new electron shell for it, so you get 1 electron on the outside. The electrons that are in the outermost shell are referred to as valence electrons. They are in the valence shell. That just means that they're on the very outskirts of this atom. But that term, valence electron, it's something you're going to hear me talk about a lot coming up very soon. Now, as I said, that second electron shell is bigger than the first one, so it can actually fit more than 2 electrons. The second electron shell can fit up to 8 electrons. Now, to see what happens when we fill up that second shell, we need to look at a much larger element. So let's take argon here. Argon is atomic number 18. It has 18 protons, so a neutral argon atom will also have 18 electrons. 2 electrons in the first shell, 8 electrons in the second shell, so we're up to 10, and then you have another 8 left over to spill into that 3rd shell. Now, if we have an atom that is bigger than argon, the electrons start filling in the 4th shell before they finish filling in this 3rd shell, which is a little bit confusing, and frankly, this is not a chemistry class, so we are going to use the following simplification to make our lives much, much easier. The first electron shell can hold up to 2 electrons. The second electron shell can hold up to 8 electrons, and the 3rd electron shell can hold up to 8 electrons. And we will not work with any elements that are larger than that, so we really don't need to worry about what happens afterward. I mentioned earlier that it is inaccurate to imagine electrons as orbiting around the nucleus of an atom as though they are planets in their own microscopic solar system. In reality, electrons move very, very fast, and unlike other kinds of particles, their position is always kind of fuzzy. So it's impossible to say where an electron is at any given time, and they move so fast that it seems like they're everywhere all at once. So when we describe the location where you would find an electron in an atom as a shell, that's actually a really good description because they're essentially an electron coating around that atom. And each electron shell is made up of 1 or more orbitals. And orbitals come in a variety of shapes, but each orbital can only hold 2 electrons max. So why can the first electron shell hold only 2 electrons, while subsequent electron shells can hold 8? Well, it's because the first shell only has this one spherical s orbital, and then the second and third shells have both s orbitals and what we call p orbitals, which you can see here. They have this kind of dumbbell shape, so you have a pair of electrons that's constantly whizzing around in each one of these orbitals. So we are officially at the teeniest, tiniest level of structure that we will ever discuss this entire semester, and from here we are going to go back up the scale and get larger and larger as we go. As I said before, in biology we really only use the top of the periodic table. And knowing what you do now about how electrons fill in on the exterior of an atom, let's take a look at a simplified periodic table one more time. The top row of the periodic table only contains 2 elements, hydrogen on the far left and helium on the far right. What do we know about these 2 elements? These are the only 2 elements that have only 1 electron shell. And how many electrons can go into that shell? Just the 2, right? So we have one atom with a single electron in its electron shell, and then another one with a filled electron shell, and then we have to start a new row of the periodic table. In the second row, we start with lithium. Lithium has 3 protons, and a neutral lithium atom, therefore, would have 3 electrons. 2 in that first shell, and then 1 left over for the second shell, which means it has 1 valence electron. So look at that. It has the same number of valence electrons as hydrogen, which is directly above it in the scale. And then we go to beryllium, which would have 2 valence electrons, and boron, which would have 3, carbon, nitrogen, oxygen, fluorine, and neon, which would have 8, which is filled for the second shell, right? So we have a full shell, and look at that, neon is just below helium, and they both have a filled outermost shell. In fact, every column of the periodic table has elements that have the exact same number of valence electrons. If we bring in row number 3, where we have the third electron shell, sodium has 1 valence electron, magnesium has 2 valence electrons, aluminum 3 valence electrons, and silicon 4, and so on and so forth until we get to argon, which you may remember we used as an example earlier, because it had all 3 of its electron shells filled all the way up. So this is what's really incredible about the periodic table. Mendeleev didn't know any of this stuff, but when he organized the elements in the way that he did, he actually was grouping them together based on these incredibly fundamental physical properties that we wouldn't understand for a long time afterward. Every row of the periodic table, elements in the same row have the same number of electron shells. Elements in the same column have the same number of valence electrons. And it turns out that it's the valence electrons that are responsible for the properties of each element. And that's why the properties were repeating in that way that we saw in the last video. All elements with just 1 valence electron will have similar properties to each other. All elements with a filled outermost shell of electrons will have similar properties to each other. And if you know how to read the periodic table like this, it's incredible that it's on the wall of every single science classroom across the country, because it's like the best cheat sheet in the world that you're actually encouraged to use during the test. With that, we conclude our discussion of subatomic particles and the structure of atoms and the periodic table and what makes different elements different from each other. And we're going to begin a conversation about chemical reactions. So don't forget everything you've learned about atomic structure, because you're going to need that information in order to understand what makes different kinds of chemical reactions work.